how far can we go with applying divide and conquer to multiplication? Actually, we can push it to its limits by considering more and more parts in the multiplication, so at least 4 numbers. And we'll now consider an algorithm of Toom, or Toom-Cook's algorithm, that generalizes the Karatsuba's algorithm. This is the algorithm that improves bit complexity of multiplication of 2 positive integers. As before, we assume that we have 2 integers a and b represented in their binary form. This time, generalizing Karatsuba and Hoffman will split these integers into k parts each. And throughout our algorithm, it is highly important that k will be fixed. Just as it is more convenient to deal with length of numbers, which is power of 2, as soon as we divide our numbers into parts and our algorithm is recursive, here our algorithm will be also recursive, and it will be highly convenient to assume that n is some power of k. So now we can split our numbers in parts, and there will be k parts in each of the numbers, so which will denote by a0 through a k minus 1 and b0 through b k minus 1. Then, as we did in Karatsuba and Hoffman, we can express a through its parts, and the expression that we get would be like a0 plus 2 to the power of n over k times a1 plus 2 to the power 2n over k, a2, and so on, and the same for b. We'll use a compressed notation by using summation operator here. Let's now look at the right-hand sides of these equations from the polynomial point of view. So we can write this right-hand side as the sum, where we put some x instead of the power of 2, x to the power of j, and where x is 2 to the power of n over k. And the same goes for b. So now we can write the product of 2 numbers, a and b. So if we denote this expression as a polynomial, say pa of x, and this expression as a polynomial, say pb of x, so now we can express a times b as product of pa of 2 to the power of n over k times pb 2 to the power of n over k. But what's great about polynomials is that we can interchange the substitution of value for variable and product of polynomials. So computing a polynomial at some point and another polynomial at the same point, and then taking the product of the resulting values is the same as first computing the product of polynomials as algebraic expressions with formal variable, and then evaluating the product of the polynomials in the same point. So if we are able to efficiently compute this product of the polynomials, then we are able to efficiently calculate this value, which is a times b. So the question of multiplying numbers now boils down to the question of computing the product of 2 polynomials. Well, computing the vector of coefficients of this polynomial product. And it turns out that here a concept of interpolation greatly helps us. So interpolating will help us quickly compute the product of polynomials. Let's recall Lagrange interpolation theorem. So suppose that we have a polynomial and we know its values in several fixed points. Let these points be tau 1 through tau k, say, and the polynomial values are p of tau 1 through p of tau k. Assume that all these are known. Then we can reconstruct the polynomial uniquely, assuming that we bound the degree of the polynomial. So if we are searching of the polynomial of the form like p of x is equal to sum of ci x to the power of I, then all the coefficients of this polynomial are uniquely determined by its values in k distinct points. And we actually can design formulas for that. The idea that we can employ here is very close to idea for constructing canonical DNF of a Boolean function. So recall that a DNF for a Boolean function can be made by looking at the truth table of the function, scanning through ones in this table. So as soon as we have 1 on some tuple of values, like alpha 1 through alpha n, we take the corresponding products or conjunction of the items x1 to alpha 1 through xn to alpha n, where this denotes x1 if alpha 1 is equal to 1 and not x1 otherwise. In this way, we are constructing a conjunction of variables and their negations such that this conjunction has truth vector exactly like this. So it's 0 everywhere except for this tuple. And now if we take all such tuples of values, and for each tuple of values we build the corresponding conjunction, then we can use this junction to glue these terms together. Each conjunction is responsible for a single tuple. This is kind of an indicator of that tuple. And then we use the gluing operation, that is junction, that allows all these indicators to bring together to actually reconstruct our function. And we will use the same idea in deriving the interpolation formula for polynomials. So we'll create a polynomial which is responsible for just one pair, like this. Let's take any tau I and the corresponding value that we know, p of tau I, and construct a polynomial which we'll call pi of x of this form. It's 1 over product of terms tau I minus tau j for all j not equal to I. Note that this is just a constant, times product of linear polynomials of form x minus tau j, where again j is not equal to I. So now let's see what happens when we plug in a value tau I for this x. So now here we would have tau I minus tau j, product over all j's, and here we have the same product. So this polynomial will be equal to 1. So it equals to 1 if x is equal to tau I. Now what if we plug in a different thing? What if we plug in tau j, where j is not equal to I? Then there will be a term in this product that will vanish on this value of x, and thus this whole thing would vanish. So our polynomial is equal to 0 if x is equal to tau j and j is not equal to I. So this polynomial is in a way responsible for the tau I value and doesn't get into the way when we plug in any other taus. So now we can just take a sum of these polynomials with appropriate constants. So p of each tau I is a known constant. We multiply this constant by a polynomial pi of x, and we sum it up for all i's from 1 to k, and thus we get an expression for p of x. So we see that plugging in any concrete tau will leave only one term in this sum being non-zero, and the value would be exactly 1 times p of tau I, and all the other terms of this sum will be equal to 0 because here we would get 0, and then they will get out of our way. And the polynomial p of x that we obtain using this formula is uniquely determined because we cannot have two different polynomials that have the same set of values, assuming that the number of points that we're considering is equal to the number of coefficients. So our polynomials have degree less than k. Now we can rewrite our pi as a polynomial for powers of x. So rewrite it as a sum of x to the power of j with some coefficients which we can denote by c Cij, where j ranges from 0 to k minus 1. So indeed, we have the product of k minus 1 linear terms here, so the polynomial will be of degree k minus 1. And our polynomial p of x is this thing. We now note that if all our taux are integers, then what we get for these coefficients are rationals. And thus each pi is a polynomial with rational coefficients. And now if we plug it in here, we get the following expression for p of x, in which we can interchange the order of summation, getting the following expression. So what we now see is that the coefficients of the polynomial that we eventually get are rational linear combinations of the values of our polynomial in our points tau I. And this is the actual corollary of Lagrange interpolation that we'll use. Given that we have fixed points and all these points are integers, the polynomial that takes these values at these points can be expressed as follows, where Cij are rational numbers depending only on taux.